Gracie, are you happy today?
I am very
I
happy.
figured you would be.
Heck yeah.
I'm back to reality with my team. So, all right. Guys, 4.4 is titled the chain rule. Volunteer want to read the essential question there today at all?
How do you find and apply derivatives of
Okay, composite functions. If you guys recall composite functions, let's just give you an example of what a composite function was again here. So, I don't know. Somebody give me some easy function for f of x. What's that again?
x plus 7?
Did you say 3x plus 7?
Yep.
Give me a g of x function.
2x plus 8.
2x plus 8. So I have a question for you then. If you guys recall way back in chapter 1 when we were looking at all types of functions for composites right here. Okay, if you remember composite functions, we said when we were working with composite functions, where did you always want to start? Inside or outside?
Inside.
I want to start on the inside and plug that in for the outside function. So what function would I really start with if I wanted to see what f of g of x was?
G.
Start with g. We're going to take g of x, which is what, kids?
2x plus 8.
And plug it in for what?
X.
Okay? So this would essentially become 3 times what, friends?
2x plus 8
Yep, you're on a roll here.
plus
Plus how much?
7.
Okay, so how do you distribute on that? They're your problem now, so
6x plus 24 plus 7.
so can I do the 24 and 7 as call it 6x plus 31?
Yep.
Okay? So what we're going to start looking at, guys, today is this. That would be your composite function from way back when. We had to evaluate those, or we had to come up with an expression for those, whatever it might have been. And they can get kind of lengthy and kind of difficult, but our job today then is this. Instead of finding a derivative for f, or instead of finding a derivative for g, we're now concerned about what is the derivative of f with respect to not just x, but the function g of x. We say that this is the chain rule is going to apply to derivatives of not just functions, but rather composite functions. Okay? So that's kind of what we're looking at today. And whether you realize it or not, a lot of the functions that you always look at are mostly composite functions. Okay? One function might be described as like x to the third plus 1. Think about that. X to the third plus 1. What's one thing I'm doing to x?
Multiplying it by. Oh, wait.
Taking it to the third power is one operation, right? And then what else? Adding 1. You're doing multiple operations. That's what's mean to be a composite function. So, guys, we're going to start looking at it in the context of what if I plug a function into another function and what that looks like for derivatives. So that's the question that we're going to talk about. By the way, what would the derivative of this be right here then after I've got my composite figured out? Just be 6, right? Okay? All right, so goal is to understand the question today, or answer the question. We've got to use the chain rule to find derivatives. We're going to use the chain rule with previous rules to find derivatives. What are some of the previous rules? Power rules, what? Quotient? Somebody say product?
Yeah,
You're really testing my ears today. And then exponentials, stuff like that, so be good with that. Then we'll look at some real life situations to solve these, okay? All right, guys, vocab, very important right here. Really, the only thing we're going to concern ourselves with is the chain rule. All right, I'll read this quickly while you follow along. It says f and g are differentiable functions, then the derivative with respect to which variable, kids?
X.
Of f of g of x is equal to f prime of g of x times what? G prime of x. Okay, no problem. We can handle this. Okay? So here's the situation. It says, in other words, the derivative of a composite function is the product of the derivative of the what? Outside and what? Inside functions. The derivative of the outside function must be evaluated at the inside function. You're like, great. What's that mean? Okay? Guys, when I told you to talk about derivatives, or I'm going to back up, I made a mistake here. I told you to talk about composite functions. You always said start where with composite functions? Start on the, and work your way out, okay? Opposite today. We start doing derivatives of composite functions. We want to start on the outside and work our way in. Okay, so let me show you what this is going to look like here today. So here we go with this. On example 1, you guys want to flip to that second page there. Okay? Using chain rule, it says find the derivatives of the following functions. All right? Can I do something real quickly up here, kids?
Yes.
See that x plus 1 to the 4th power there? If I would expand that, that would be x to the 4th plus, I've got to think on this, 3x to the 3rd times 1 to the 1st plus 3x squared. No, this would be a 4 right here, wouldn't it? This would be a 6. 4x to the 1st plus 1. If I took this whole function right here and expanded it, could I find a derivative that way?
Yeah.
What would that equal then? What would f prime of x or y prime in this case be?
4x to the 3rd plus 12x squared plus 6x.
Careful.
Oh, 12x.
Yep.
Plus 1.
Okay, hold that thought for a second, okay? Guys, chain rule would say this. It would say use your rules of derivatives. It would say use your rules of derivatives right here to find this. And the way we want to do this is chain rule. Now, chain rule would always say start on the, what did I just tell you? Outside, work your way in. So it's the derivative of this right here. You guys don't have a power rater, so isn't this like a power rule right here?
Yeah.
Where do you think that's going?
The front.
So we're going to call this y prime equals 4 times x plus 1. But by power rule, what's going to happen to your power?
It's gonna be subtracted. Like, it's gonna be 3.
Cubed, right? Then
Yeah.
take this times the derivative of what's inside. The part that's inside is the part in the parentheses that's inside. So that part that's inside is simply x plus 1, isn't it? My friends, what is the derivative of x plus 1? Just 1. Okay? Now let me show you something. I know I'm going through some stuff that's prior knowledge to you guys right here, but let me show you this right here. This x plus 1 to the 3rd power, let me show you what that becomes. That is going to be, by binomial theorem, x to the 3rd plus 3x squared plus 3x plus 1. This part in parentheses to the 3rd power is that mess right there. But what's this getting multiplied by? 4. Okay, help me distribute everywhere. What are we going to get here?
Yeah, 4x cubed plus 12x squared plus 12x plus 4.
Talk to me about the relationship of what we just did with chain rule and what we would have known if we would have expanded and done our prior rules of derivatives. What's true about those two expressions? Exactly the same. So does the rule work? The answer is yeah. Okay. Chain rule. Let's make a note up here. Start where, kids? Inside or outside this time?
Outside.
Okay. And start outside. And work in. Now, guys, I would probably tell you, you know, the 1 times 4 obviously is 4. I'd probably say leave y prime as 4 times quantity x plus 1 cubed right here. That's probably what I would do. There'll be some necessary points down the road when we get to optimization where we may want to expand it. I'm not really sure that's going to be necessary, but guys, this is going to be considered some kind of a factored form that we're working with right here. And when we're dealing with factored form, it's going to help us solve for x's so much easier. So I would probably encourage you to leave what you have instead of expanding stuff this time, okay? Make sense, everybody? Anybody brave enough to try the next one? At least start me. What am I doing here?
3's going out to the front.
Okay, so we have the quantity 5x minus 4 to the 3rd. Where's that 3 going, minions?
To the front.
To the front. 3 times 5x minus 4. Power?
Squared.
Squared. All agree with Ellie?
Yep.
Okay. All right, so we've dealt with the outside part. We've brought that exponent out to the front. We've lowered the power by 1, but now we've got to deal with the derivative of an inside part, which is 5x minus 4. What's the derivative of 5x minus 4 going to get me, kiddos?
5.
Times 5, yeah. Boom. There it is. Now how about this 3 and 5? Can I do something with that? Yep. So probably call this what, kids? 15.
15 times 5x minus 4 squared.
Very good. Derivative of that would be 15 times the quantity 5x minus 4 squared. How in the world am I going to handle part C? I don't see a power there.
It's to the
There it is.
So call it 1/2 power?
Yep.
All right, so let me make some room here real quickly.
Wait, that's the answer?
That's the answer.
Oh, you don't have to expand?
Do you want to expand it?
No, I just thought.
I mean, we can expand it because doing expansion is a lot of fun. I like to do that in my free time at home.
It's alright.
No, and Ellie, let me tell you why. Okay, leave it like that because here's the deal. When we get to optimization and stuff right here, we're going to be setting a lot of derivatives equal to 0 down the road. Okay, and when we set stuff equal to 0, it's much easier to solve for excellence in this factored form like this instead of expanded form. So
Okay.
when we have something that looks like factored form right here, that's a good thing. That's a win for us. Okay.
Alright.
Sound like Vikings football right there. All right, this play is not in their playbook. Okay, good with that?
Yep.
They win this week.
They lost again. I shouldn't say they got beat by another team. They're so good at shooting themselves in the foot. It's just bad. Okay? They gave up like 17 points on turnovers yesterday. But hey, you know what? Here's my hope. If the playoffs started today, they'd be in. And you know who they'd be playing today if they started the playoffs today?
Wait, the playoffs are already started?
No, you're not hearing me right now, okay? You're not hearing. If the playoffs started today, they'd be in. They'd be facing the Packers in the first round if it started today.
I was
Did you see the
gonna say,
video
I
of
don't
Kirk
know
Cousins
what
trying to line up under center?
Yeah, I did. I'm gonna hear about that for a while, I'm sure. Okay. Hey, before I went off on a football tangent right here, kids, what did you say raise this to?
1/2.
So let's call this 3x plus 9 to what power, friends?
1.
Okay, I'm done talking. You tell me the derivative on that. What's g prime of x gonna be?
So, 1/2. Gonna get rid of the
1/2. So you're pulling that out front, is that what I'm hearing, kids?
Yeah,
Okay,
and then it'd be, times 3x plus 9 to the negative 1/2.
okay, so 3x plus 9 to the negative 1/2. Whoops, come on, work. All right, are we done there?
No,
No.
times 3.
Times the derivative of what would be inside, right? Okay, so how about that 3 times half there? Could I call that 3 halves?
Yeah.
I could do that, couldn't I?
Yeah.
And then, how about that last part with the negative exponent? Do you want that negative exponent to exist up top or in the bottom? But if I move it to the bottom, what should I probably do with that negative half exponent?
Just make it a.
Okay, make it a, it's really kind of like it's up top here, the way it sits out here. So if I want this to move to the bottom, what's gonna happen to that sign?
Gonna be positive.
Okay, so watch what happens here. This is gonna be 3/2. Do we understand the 3/2 part?
Yeah.
Okay, that's the 1/2 times the 3, isn't it?
Yeah.
Okay. Now if I move this 3x plus 9 to the bottom, that would be a 3x plus 9 to what power?
1/2.
1/2. But taking something to the 1/2, what's that look like? What sign or what symbol?
Square root.
Square root here. So it'd probably be over the 2 times the square root of 3x plus 9. Okay. Now again, questions gonna come up. There's no expansion to do there, but do I have to do that? I would strongly suggest against doing that, okay? I'd say once you've applied it, call it good right there. I don't think they want to listen to this anymore.
Scared of
Yeah, I'm good at that. Okay, good with that? All right, let's try a couple more here. You guys are up. Y prime.
2 times 3x squared plus 2x times 6x plus 2.
Yep, there it is. Everybody understand 2 out front?
Yep.
Inside stays the same. Power of 2 becomes a power of
1.
1. Derivative on the inside of this part. 6x plus 2, right?
Yep.
How you guys feel about that? Yay, nay? Maybe? Okay, you guys try the next 2 on your own. See what you come up with. When you've got them, check with the neighbor around you, see if you agree. supervisor or from
Advisor.
Win today? Advisor today? That's not what I wanted to hear. We're ready on E right here. I don't like the way E is written. I'd probably write this as f of x equals what first here?
X minus 3 to the 1/3.
Okay. Anybody want to take a shot at it?
One third gets moved to the front.
And then x minus 3.
And then negative 1/3.
2/3, right?
Or 2/3.
Yep.
Yep.
Okay. Then times the derivative on the inside, which would be what, kids?
Just one.
Just 1. So pretty much done right there, right? Now, if you wanted to write this, you could probably write this as 1 over 3 times, okay, kids, I'm gonna put the x minus 3 down here. Kids, what would probably the index be up here based on this negative 2/3? And then this quantity would be to the second power down there, if you wanted to write it that way, okay? I think that was a little more difficult than the last one there. Anybody want to take a shot at the last one?
3 times x squared plus 4 squared times 2x.
Very good. And some people might take this 3 and 2x and put it together. So they might call it 6x in the end right here. They might say, well, or I could call it 6x times x squared plus 4 all to the second. Okay. And if I back up and look at this one, would it have been possible to take 2 times this one here?
Yeah.
Pretty easily, right? And then people might FOIL that out, but if you leave it like that, I'm okay with it. I guess the point I'm trying to make is when you do a derivative, they might try and expand some things, which I'm probably saying, probably not a good idea. If you're checking answers in the back of the book or back there, your answers might not look exactly like that in the end, okay? But if you do check them back there with that, you can at least see that they got this far. So if you see at least this part in it, then you'll know you're on the right track, okay? By the way, I don't know if I told you this or not, guys. I don't think I told you guys this. Just last week, I went ahead and in the web page here from now on, at least in this chapter, there's a drop down by menu. See where it says Chapter 4 Solutions?
Mm-hmm.
Just got to find the right section. Okay, so they're in there for you now, if you want to check them, okay? Make sense to everybody? And I like these, again, I don't want you to just to copy them down and get them done to get points, but they're there to make sure you know you're on the right track, or if you get stuck somewhere, because I know what's going to happen, okay? All right. Guys, how you feel about chain rule application so far? Now, just because we learned a new rule, does that mean forget about everything else that we have? No. Okay, and example 2 says you're actually going to use the chain rule with what? Product rule. This is an interesting one. Okay, all of a sudden, guys, we start running into situations where we might have, okay, I'm just going to highlight some things. You guys see this part right here that's highlighted in yellow?
Yeah.
Isn't that something that looks like the chain rule application? But that's getting taken times what value or what expression? Okay, so we've got some chain rule in there, but that chain rule is also being multiplied to another expression. So this becomes a combination of chain rule with product rule. So if I'm using chain rule and product rule right here, well, guys, if we're using product rule, we better assign U and we better assign V. Okay? So what's your guess on what U equals?
X squared minus 8 to the 3rd.
So x squared minus 8 all to what power?
To the 3rd.
And then what's that make V?
2x.
Okay. All right, so we've got U and V assigned. We've got them split up. They're getting multiplied to each other. Okay. Do we know enough now up here to find the derivative of U?
Yeah.
So what's u prime gonna equal, friends?
3 times x squared minus 8 to the second times 2x.
Okay, and I'm probably gonna combine that 3 and 2x. Is that all right with you guys?
Yeah, so it'd just be 6x.
Yeah, I'm gonna call it 6x. That's just these two on the ends, the 3 and the 2x. I'm gonna call it 6x times x. What was it? X squared minus 8. All to the second. So I'm gonna use this as my v prime. I'm sorry, my u prime. My u prime. I'm gonna use this as u. Guys, v is pretty simple. What's v prime easily gonna be?
2.
Okay, I forgot the product rule, kids. The turkey must have gone to my brain. And I don't remember anymore, gobble gobble.
Oh, it's u prime times v.
U times, u prime times v, you said?
Yeah.
Okay?
Plus u times v prime.
U v prime. Every time I'm outside in the pool at my house, they're like, what are you doing, Dad? I'm getting my UV prime on. All right, never mind. Bad. Getting some rays, ultraviolet rays, in my prime, 46 years old. Never mind. How many times do you walk out here and think the old man's lost it? Every day?
Some days.
Some days, okay? All right, here we go. What's u prime, kids?
6x times x squared minus 8.
Okay, we're going to take these two times each other, right, guys?
Yeah.
Do you think it's okay to take 2x times 6x here?
Yeah.
What's 2x times 6x going to get me?
12x squared.
12x squared, right? I'm going to call this 12x squared. That's coming from this times this. So the 12x squared times x squared minus 8, all to the second power. Okay, do you understand my u prime v there? First question.
Yes.
And what's that going to get added to now? uv prime, which I'm probably going to put the 2 out in front. Is that okay? So it'd be these two, right?
Mm-hmm.
So 2 times, how about x squared minus 8 to the third? There it is. So our derivative f prime of x is right there. Okay. Guys, I know chain rule's new, but is there anything very different than what we've done so far? Are there going to be times where you need to take all your rules and put them together, make them work? That was an example of that right there, okay? All right, are we on the third page yet?
Yep.
All right, any questions up to this point right now, friends? Feel pretty good about it? Cool. All right, what's on the third page? Oh my gosh, let's see. Oh no. Find the equation of a line to f of x equal 3x minus 1 cubed at the point where x equals what?
2.
Well, guys, anytime we've written a tangent line, those are straight, right? Tangent lines are straight, right? So we would need to know its slope and a point, right? Okay, is there an easy way to find the point?
No.
How do you find the point we want?
Plug 2 into the equation.
So our point would be f of 2, right? What is the x value we're concerned about? 2. Okay, so let's figure out what f of 2 is. This would equal 3 times 2 minus 1 all to the third power. What's 3 times 2?
6.
6 minus 1, 5 to the third.
125.
You guys agree that this is the point 2 comma 125? When I insert 2 into that function, the output is 125. So if I would graph 3x minus 1 to the third on decimals, and I typed in x equals 2, what y value would it cross the function?
1.
So that point that's on the graph, that 2 is 2 comma 125. We all agree there?
Mm-hmm.
Okay.
Next thing we need to know then is what's the slope at that point. And if I want a slope at that point, we need to know the derivative, right? So to find that, so we got to find our slope. So our slope really is the first derivative at what x value again, kids? So f prime of 2 is what we're after. Well, kids, help me out with the derivative of this by chain rule now. What's the derivative going to be?
3 times 3x minus 1 squared times 3.
All agree that that's the derivative? Pull the 3 out front, lower the power. Keep the inside function the same. Then you're going to go times g prime of x, or the part that's inside. Okay? Okay. This 3 times 3 would be 9, wouldn't it, kids?
Yeah.
So f prime of 2 shall become 9 times, what's 3 times 2 going to get me? Okay, so this will be 6 minus 1 here, which is what? What's 5 squared?
25.
So what's this really, 25 times 9 when I plug 2 in? And 25 times 9, I'll tell you, is 225. So, sounds like to me, we're passing through which point? What comma what? 2 comma 125 with a slope of how much?
225.
So our tangent line equation, let's start it out this way. I'm going to start as y equals 225x plus some y-intercept. Don't know what that is. Have I got the slope in the right spot, kiddos? Absolutely I do. That's perfect, isn't it? What else do we know then beyond the slope?
Point. 2, 125.
2 comma 125 is the point it passed through. States when x is 2, your y value is what?
125.
Okay, so we're going to call this 125 equals 225 times my x value that we're at, 2, plus b. My North of Highway 3 math skills tell me this is 125 equals 450 plus b. Talk to me, friends. What are you doing next? Subtract the 450. I have no idea what that is. Negative 325. Thank you very much. Kids, what's the equation here?
Y equals 225x minus 325.
So 225x minus 325. Now kids, I will tell you this every time. If they ever say, give me a tangent line equation, I would say go in there and see if your work is right. I would graph this every single time to know if I'm right, okay? Do you think we're right? I think you guys are perfect on this, okay? All right, but let's just check here, all right? First question, who needs more time with this? Anybody need more time with this? Are you okay? We've done tangent lines a lot this year, haven't we? Okay, it just pops up at different times. And this time we're looking at it relative to a derivative of function that we had to apply the chain rule on, okay? So I'm going to run into decimals real quickly. I'll leave this kind of up here maybe. Oh, decimals, where are you? All right. Guys, what was the original function? Was it 3x minus 1 all to the third? Okay, I'm going to squeeze this down because I know the point we're working at is 2 comma, what was it, 2 comma 125? Or? So I'm going to type that point in 2 comma 125. Is that on the graph? Well, that's good, isn't it? What did we come up with our equation for a line of tangency then?
Y equals 225x minus 325.
Guys, does it look like we got a line of tangency there at that point? Okay, if I click on the green line in this, looks like they're all going to meet, okay? I'd say we nailed it there, all right? Okay. Guys, this chain rule bit. Start where this time? Not on the inside, but start on outside derivative times inside derivative. That's all you're really doing. Outside derivative times inside derivative. Okay, let's take a look at some more here. I don't know, maybe I can try and confuse you some more. Example 4 says, oh my gosh, using the chain rule not to find just the first derivative, but that darn second derivative. What's the second derivative tell you again? Acceleration if it was relative to position, absolutely.
Concave up,
Or concave up or concave
down.
down. You bet. Good, guys. Well, I can't find the second derivative unless I find the what?
First.
Better find the first. Okay, here we go. Let's find f prime of x. Okay, what's f prime of x?
3 times 5x minus 2 to the second.
Times 5.
So I'd probably call this 15 times 5x minus 2 to the left. Okay. Now guys, does this look like a product rule to you? Kind of. But here's the deal. Since there's just a 15 out here, I can treat 15 as u and treat this part as v right here. But since 15 is a constant out here, 15 is just going to stay out here by itself. The only part I would really need to differentiate now for f double prime, since that's constant. Now, if it was like another function, like 5x, then you'd have to use u and v. Okay, but the reason you don't have to use u and v on this right here, what's the derivative of a constant 15? 0. So when we end up with u prime times v, u prime would be 0, times v would just be 0. And then if you did u times v prime, that's just going to be this times whatever derivative this is. So if you ever have a constant out front, just treat it like it's its own entity, all right? So f double prime of x, here we go. It's going to become 15 times, all right, help me differentiate that part in the box. What power? Times what's inside.
5x.
Just the derivative of what's inside. So just 5, right? Okay, how about 5 times 2 here? 10 times 15 more would make what? There's f double prime of x, kids. Okay, what do we want to evaluate? The derivative where? Well, do I already have the second derivative? So what type you plug it in for x?
2.
So f double prime of 2 is what I'm after. That becomes 150 times 5 times 2 minus 2. Okay, so help me kids, on inside of parentheses 5 and 2 is 10 minus 2 more makes 8 times 150. Oh my gosh. 800 and 400. 1200?
Sure. Yeah.
Does that sound right? Somebody take 8 times 150. I think it's 1200. I did 8 times 1 and a half. 8 and half of 8 is 4. 8 4 is 12. Add 2 zeros is 1200.
Yeah, sounds about right.
You guys are easy to get along with. I say something like, yeah, that's all right. Okay, so maybe I'll say this. Can I have $1,000 for everybody? I thought I'd try. I thought I had you right where I wanted you. And it was going to be easy. Okay. Guys, how you feeling about this chain rule stuff so far? I have uno more examples. Okay, get a real life app here. Guys, really, you need to remember, start on the outside times the derivative of what's inside. Derivative out, derivative in. Derivative of the outside times the derivative of the inside. Derivative of the outside times the derivative of the inside. Hammer that home, okay? I want to walk through the hallways and hear you saying that today, okay? So like I go through 4th hour and I see Gracie Rathley walking through and she's saying composite function derivative. Derivative of the outside times the derivative of the inside. And when people look at you like you're weird, you'd be like, that's what I'm after right there, okay? Aye, this looks terrible. Imagine we're moving straight upward in a hot air balloon. Let y be the distance from the ground. What happens to the air temperature as you move higher and higher up?
Goes down.
Goes what?
I said goes down.
Goes down. Anybody know why that's true?
That is a weird concept because heat rises.
Because the sun can't, the like heat from the sun can't go through the atmosphere at that level. Something like that. I don't know. My mom tried to give me a science lesson.
Does it have to do with pressure at all? Because obviously, you think about the mountains. Think about mountains. Isn't it colder at the top of the mountain than it is at the bottom of the mountain?
Yeah. It has something to do with the atmosphere.
Does it have to do with something of density of air?
Yeah.
Green.
Really? Because think about it. Anytime you guys get on an airplane, what do they do to the cabin before they take off? Well, they pressurize it because the air density is less up top than it is down here. So they gotta put that pressure in there so as you get up there, you're not like, let's see, up there, if the pressure was less, you would explode. So you would just be like a big old, you'd be like a marshmallow in a microwave. Okay? Okay, so the temperature H is changing as a function of altitude, so H equals F of Y. So the temperature H equals F of Y. How does our temperature change with time? Okay. Well, in this case right here, it says, how does our temperature change with time? So if we're moving straight upward, what's happening to the temperature? Okay, temperature is falling, right? Which would imply then that if H is equal to F of Y, the temperature of a certain altitude Y, then F prime of Y, would that be a positive value or a negative value? Temperature's falling, it'd be a rate of changes, decreasing, right? Negative. Okay. Says since temperature is a function of height, F of Y, and height is a function of time, Y equals G of T, we can think of temperature as a composite function of time. H equal F of G of T. Okay, so again, G of T is a function of our height, and then F of Y is going to be a function of our,
Time.
okay? So it says H equal F of G of T with F as the outside function and G as the inside function. The example suggests the following result, which turns out to be true. Okay, so it says the rate of the composition of a function equals the rate of change of the outside function. Okay, that would be the F of T, right? Or in our case, F of Y, wouldn't it? That would be the temperature times the rate of the inside function times what? Okay, there's really nothing here other than to say that this is really the rate of the outside function times the rate of the what? Okay, and guys, anytime we talk about rate of change, that's really the what? Derivative or slope, right? Okay. So when we talk about this right here, this H equal F of G of T right here, isn't this a composite function right here? So the rate of change for this then, my friends, the rate of change of composition of the function would be the outside function, F prime times G prime. Okay, all this is an application to which rule again? So all you need to remember today, guys, is this. If you're going to apply the chain rule, it's the derivative of the times the derivative of the inside. All right. Stop this here.